How does statistical mechanics apply to real systems? Imagine trying to understand how millions of tiny particles in a glass of water behave without watching each one. That's where statistical mechanics comes into play. It links the tiny world of atoms and molecules to the big properties we see, like temperature and pressure. Instead of tracking every particle, it uses probability to describe how they behave collectively. This approach is necessary because knowing the exact state of every particle is impossible due to their huge numbers and complexity. Instead, it assigns likelihoods to different microscopic states based on the total energy and other factors. From these probabilities, it calculates observable properties like energy, pressure, and heat capacity. For example, temperature is understood as the average kinetic energy of particles, and pressure as the average force they exert when they collide with the walls of a container. This method bridges the gap between the tiny laws that govern individual particles and the thermodynamic laws that describe real systems. It explains how phase changes happen, like when water freezes or boils, by modeling how particle interactions shift. It also helps describe the behavior of solids, liquids, and gases, including complex materials like liquid crystals or granular substances such as sand. Statistical mechanics is fundamental in understanding entropy, which measures disorder or randomness in a system. It shows why systems tend to move toward states with higher probability and more disorder, making processes spontaneous. This concept is key to explaining why heat flows from hot to cold and why certain reactions happen naturally. Beyond physics and chemistry, statistical mechanics finds uses in fields like materials science, biology, and even economics. For example, it helps model how diseases spread or how large groups of interacting elements behave. Researchers also use computer simulations based on these principles, like Monte Carlo methods, to predict how microscopic behaviors lead to macroscopic properties. By focusing on averages and probabilities, statistical mechanics makes the principles of thermodynamics easier to understand and apply to real-world situations. It shows how the collective behavior of countless particles results in the predictable properties we observe every day, making it a powerful tool for explaining the physical world.